Very good morning or good afternoon to all of you. I'm Dr. K. Prasanna Lakshmi, Associate Professor in the Department of Mechanical Engineering, JNTU Hyderabad from India. I'm here to talk about the evaluation of mechanical and wear properties of the aluminium hybrid nanocomposites with the additions of the silicon carbide or graphite. So here, as we all know, the composite materials, it is having a very high demand in the market now. So a small research is being done on the composite material, which consists of the aluminium 7075 with the addition of the silicon carbide and graphite. And it is called as hybrid composite. And we are going to find out the wear performance. So the analysis demonstrates the effectiveness of the graphite presence in the matrix to minimize the wear. And the hybrid metal matrix nanocomposites were manufactured by a powder metallurgy process by reinforcing the graphite at different weight fractions. So the graphite was taken with 0%, that means complete only Al7075 base metal. And again, 5% of silicon carbide is added. And again, 5% of graphite is added. For the same combination, 10% of the graphite is added. So the addition of silicon carbide is fixed at 5%. So in this process, the density, toughness, microstructural analysis and wear performance of the prepared hybrid nanocomposites have been analyzed and it is investigated. So the density and toughness of the reinforced composites have been improved with the incorporation of the reinforcement when compared to a monolithic alloy. The significant increase trend in mechanical properties and wear performance of the aluminium hybrid composites was accomplished by the addition of the silicon carbide in the graphite particles. So here, as we know, the current engineering applications require the materials that are stronger, lighter, and less expensive. A good example is the current interest in the development of materials that have good strength to weight ratio and which is suitable for the for the automobile applications where fuel economy with improved engine performances are being more and more critical. So the performance of metal matrix composites are mostly dependent on selecting the right combination of the reinforcing material since some of the parameters are associated with the reinforcement. The authors also have reported the volume to weight fraction and size of the reinforcing particles, which plays an important role in controlling the porosity level. The most common metallic alloys generally utilized are very light weight metals like aluminium, magnesium, titanium. And the alloys used are sometimes zinc and copper, and stainless steel also being used. But silicon carbide and aluminum are the most commonly utilized compared to the other synthetic reinforcing particulates. Basically, here we are going to find out the strength hardness, where we want to improve the strength and we want to improve the hardness also. And again, not compromising for the ductility and the fracture toughness. So that means an optimized value has to be found out. And that we have done through the Taguchi technique, where we have taken many parameters and then we have varied some of the values. And then we could find out the signal noise ratio. Then finally, we could get one optimized value. This is all running around the wear loss. So we are trying to minimize the wear loss. And we are trying to introduce the graphite for good lubrication purpose. So here, these have necessitated the use of 2 or 3 synthetic reinforcing particulates for the proper optimization. So the main objective of the research is first of all, we have to fabricate, and then we have to characterize the hybrid composites by using some of the devices, optical microscope and SEM analysis. And then we have to evaluate. And then again, the analysis is being done and testing is being done on the sliding conditions. Then we could get some conclusions. The experimental procedure says that Aluminium 7075 is taken, and the graphite and silicon carbides are being added as a powder using the powder metallurgy technique in the ball milling machine for 60 hours, and it is compacted under a pressure of 700 megapascals. And then afterwards it is vacuum sintered, and then after vacuum sintered, we could get the density, hardness, wear behavior, and we could see the microstructures using the scanning electron microscope and OM microscope. So the powder metallurgy route is one of the promising method to vary the percentage of reinforcement and avoid the unnecessary formation of the phases. So here the main thing is because it is completely at same temperature, all the powders are being blended. So we don't come across any kind of phase differences. So phase differences is the main criteria, or it is the main reason for the cracks and the other defects. So which is completely avoided here. So powder metallurgy makes sure that whatever the powders we are trying to blend and we are trying to compact and we are trying to sinter, it is going to give the uniformity of the bonding. Uniformity of the structure is being attained. So the ball milling operations, ball milling parameters are the powder to ball ratio is 1:10. So vials L ball materials are taken as the tungsten material, and the speed is taken as 300 RPM within a duration of 60 hours. It is being soaked, and the medium uses toluene. So here, basically, how the preparation of the hybrid composites take place. So before processing, all the powders are basically preheated so that all the moisture can be removed. And then a required composition of the aluminium 7075 and the required composition of the silicon carbide and the required composition of the graphite is being blended. It is being blended in a high energy ball milling using the tungsten balls with 10 to 50 mm balls. The ball to weight ratio is anyhow, it is 1:10. And the milling period is taken for about 60 hours. So finally, the blending and exemplary grinding procedures were done at 300 RPM to prevent the oxidation or the sticking powder on the vial wall using the toluene medium. So here we are using the optical microscope, OM microscope, and that is metallographic analysis can be done here. And then we are again using the scanning electronic microscope to find out the microstructure levels, and it can be characterized clearly. So here you can see AL7075 as a base metal. You can see the microstructure, and if 5% of silicon carbide is being added, we can see the density. You can see how the density is varying, how the grain size is varying. Here also we have taken 5% of graphite, and the second figure shows the 10% graphite. You can see the grain structure difference. Here, the blended powders were compressed under the 700 megapascals. But before every test that is being done, a zinc stearate is used to lubricate the die walls, and then it forms the green compacted samples. These were soaked at a temperature of about 300 degrees centigrade for 10 minutes. And again, it is soaked for another 180 minutes at temperature of 600 degrees centigrade, and then it is cooled. And then the samples are then systematically prepared using the different categories of the coarse and fine abrasive grit sizes. Then the sintering process is being done. The sintering of the powder sequentially involves the establishment and growth of the bonds between the particles of powder. At their areas of contact and migration of the grain boundaries formed at the bonds. The green compacts were sintered in vacuum furnace at a closely regulated temperature of 600 degrees centigrade, where it took 60 hours for completing the sintering process, and it is allowed to get cool to room temperature in the furnace itself. And then we could get some specimen sizes. and the abrasive paper grades of 600, 800,000. So here it is shown in the form of the graph. We can see here. The temperature is increasing as the time is increasing. Again, the temperature is maintained constant. Again, it is increasing. So these are all the soaking time when the temperature is slowly increasing. And then again, it is soaked. And then finally, it is allowed to cool. So here you can see the temperature is drastically decreases because it is allowed to cool in the furnace. Right. So how do we get some kind of, we can fetch the result by using the microstructure of the AL7075 hybrid composites. So here you can see the 5% graphite and 10% graphite after sintering is being done. So here you can see in the 5% graphite, it is observed that the graphite microparticles are with tiny oxidized particles present at the worn out areas. So which ensures that the small particulates are well packed together and generates an adhesive layer across the surface. So here you can see all these adhesiveness you can see here. So as a result, the print surface deformation due to plasticity is significantly reduced. So which is actually not a desired one. So it has to be reduced. So it reduces drastically. Whereas if you use the 10% graphite microstructure after sintering, it shows the loose particles at the work surface, demonstrating the worn out surface severe deformation. So wherever the worn out surface takes place, here the deformation is severe. So you can see the difference in the microstructure if it is 5% graphite and at 10% graphite is being added. So here the microscope examination finds that homogeneous reinforcement dispersion and robust interfacial bonds between the particles and the matrix are formulated, contributing to the excellent friction and wear characteristics. So as coming to the wear mechanism, the SEM examinations of the worn out surfaces were shown in the figure, whereas the standard SEM images of the sintered samples of aluminium with 5% of silicon carbide, here the composites wear behavior, it shows the wear produced by the deeper stable strips and the breakage of its oxide film, thereby resulting in the rise in the wear loss. So it demonstrates that the 5% silicon carbide was subjected to the considerable significant plastic deformation. So this is, I'm talking if till the graphite is not being added. So once, because it is undergoing the plastic deformation, once we try to add the graphite, which gives a lubricating effect. So here it has more good patterns on the mild plastic deformation at the groove boundaries. So these graphite reinforcements provide more smoothness to the substrate surface. So whereas 10% graphites, the microstructure, it shows a significant wear characteristics. So graphite particles disperse throughout the aluminum matrix, which help to reduce the wear particles mean size. Conversely, the hybrid composites wear debris, mixed cores and fine particles with non-uniform patterns. So the mechanism is characterized as forming a series of deep grooves due to ploughing action, where worn debris hardens and asperities crash deeply into the composites counter discs. So these characteristics slow down the increase of temperature increase during the wear process, which reduces the composites interface adhesiveness. So here are some of the worn out characteristics that is being found out by using the 5% and 10% graphite. And whereas in 5% graphite, it was observed that the graphite microparticles with tiny oxidized particles present at the worn out area. And further, it ensures that the small particulates are well packed together and generates an adhesive layer across the surface. So as a result, the plasticity is drastically reduced. So because of this, its temperature rise was decreased, and this way the soft graphite particles combined with retained loose debris forms a graphite-rich tribo layer on the work surface. So thereby the excessive wear can be reduced. So the 5% addition of the 5% graphite is giving us the optimized value, because if the lubrication is more, if you are using the 10% graphite, it is going to damage the layer. The smoothness will try to damage the layer, which we don't want. So that is tribal layer on the work surface may not be that optimized value. So thus the excessive wear will be reduced, and the abrasion, delamination are the predominant sources of the wear. So as far as the density is concerned, as a single aluminium 7075, it has got 2.81, and if you are trying to add the graphite 0, 5%, 10%, with the fixed amount of 5% of silicon carbide, the density goes on decreasing. So, and that means there is a decrease in density with the increase in graphite reinforcement. So here the lower density reinforcement of graphite can be concluded. So as far as the hardness is concerned, hardness also decreases as the graphite content is being increased. And when you are trying to find out the effects of the applied load, so here you can see the wear loss and the coefficient of friction. The graph is being drawn by varying the load and the sliding speed. Sliding speed and sliding distances are being varied, and thereby we can find out the variation of the applied load with respect to the wear loss and with respect to the coefficient of friction. So here you can see as the applied load increases, the wear loss also increases. And in the second figure, as applied load increases, the coefficient of friction also increases. So here we can see as the coefficient of friction is actually decreasing for the 10% graphite, it is little more for the 5% graphite, and it is further more for the single base alloy. So coefficient of friction decreases with the increased percentage of the graphite. Similarly, you can see the effect of sliding speed. So here you can see the figures on the y-axis for the wear loss as well as for the coefficient of friction. So here the sliding speed with respect to coefficient of friction and wear loss, it changes. It is changing. The wear loss is changing, but not very significant. It is very, it is almost nil. You can say it doesn't affect much. The sliding speed and the for the wear loss with respect to coefficient of friction doesn't affect much. ANOVA is another software wherein you can find out the responses. You can find out the responses of the various parameters with a null hypothesis for the test where the means of different groups are equal. So this is called as ANOVA, and here we can find out the signal noise ratio for the wear loss using ANOVA. So the various parameters taken are reinforcement, load, sliding distance, and sliding velocity. And the percentage of contribution also we can see. Similarly, we can find out the signal noise ratio for the coefficient of friction with the same parameters, the reinforcement, load, sliding distance, sliding velocity, so that you get the signal noise ratios and we get the percentage of the contribution. So similarly, we can see the same thing on the graph also. Here you can see the main effects plot for the SN ratios. So on the y-axis, we are keeping the mean of the signal noise ratio, and with respect to reinforcement, load, sliding distance, and sliding velocity, you can see that reinforcement and load varying in the load and varying in the reinforcement. It is the signal noise ratios are varied significantly, whereas sliding distance and sliding velocity are not at all varying much. Similarly, coefficient of friction also you can see the same pattern, whereas the reinforcement highly influences the signal noise ratio as well as the load. So here you can see the conclusion. Here also one more, we have found out the signal to noise ratios for the wear loss. So generally we want the wear loss to be lesser. So the smaller the better. By changing various parameters, like reinforcement, load, sliding distance, and sliding velocity, we have taken the L16 level and using Taguchi technique, we could get the optimized values. Similarly, we can find out the signal noise ratios for the coefficient of friction also. So here also we have taken the 4 level, that means L16 and orthogonal array, by which we can find out the optimized value. So coming to the conclusion, the development of hybrid nanocomposites of uniform distribution. It is being used through the method of photometallurgy, and it were validated with the scanning electron microscope and the optical microscope morphological images. As the percentage of graphite in hybrid composite increases, the density and hardness values decreases. So these were the results that were seen. As the percentage of graphite is increasing, the density and hardness values decreases. Already we have seen in the graph. So the incorporation of SiC reinforcement, it increases the wear resistance, and the wear losses are also improved. Wear losses are improved means the wear losses is decreases. The 5% graphite involvement, it decreases a lesser value, and 10% it further decreases. So wear resistance is better than the base metal, and the amount of graphite released on the wear surface increases the percentage of the graphite addition increase. Yeah, and the Taguchi method design of experiments, DOE. So we have used ANOVA software. So where we can get the most significant variables affecting the sliding wear of the composite. So these are the basic percentages for whatever we have done. We could find out the investigations, the values of the applied load and the percentage of the reinforcement content and the sliding distance and the sliding velocity. So ANOVA also showed the most significant variable affecting the friction behavior of the composite. And the basic thing is, however, the sliding distance, sliding speed had only very slight influence on the wear loss, whereas the applied load and weight fraction of the graphite had significant effect on the friction coefficient of the composite. So here are some of the references I have taken. Right. Any questions regarding the hybrid composite materials? So I may not be present online, so please feel free to, any questionnaire is there, please feel free to put me a message in my mail. I'll be happy to respond. Thank you.